So I'd like to preface my presentation by telling you about an event that happened 3 years ago, almost to the day actually. A friend of mine and former boss called me and said, I'm working as a hospital manager now, and I would like you to come work for me. I need a guy like you. So I said, yeah, sure. What about the job? Can you tell me a little bit more about the job? Well, you're about to extract some data. Okay, what kind of data? It's it's medical data. Okay, okay. Do you have some more information about this? No, I don't have that. So what then happened was I took the job, obviously, and then I got the assignment to extract medical data from Linköping's University, PAX and LIS, and that means Picture Archiving System and Laboratory Information System. And what I thought would be very easy turned out to be very, very hard. And I'm going to talk a little bit more about that right now. So my name is Pettersson. I work as a system developer at Region Östergötland, and I specialize in IT infrastructure and data integration and automation processes. I focus on healthcare and research sectors since 3 years ago, I should add. I have been engaged in the IMI-funded Big Picture project since 2021, as I told you, and working within a work package called Work Package 3 in the Big Picture project. My focus is on the development of extraction tools, metadata standards, and supporting infrastructure to enable large-scale medical data collection and analysis. So the Big Picture is a major project, and it's aimed at creating a huge repository of pathology data. With this data, we are trying to build the largest repository of pathology data in the world. And Work Package 3, where I work, plays a pivotal role in the project, focusing on collecting large data sets from multiple beneficiaries all over Europe and ensuring that data supports broader innovation efforts. And Work Package 3's primary goal is to establish a sustainable network of nodes, where each node represents a partner or beneficiary responsible for contributing data to the Big Picture repository. Another key role of Work Package 3 is mediating and facilitating the data collection process and ensuring that the data from each node is accurately and efficiently integrated into the central repository. This will help create comprehensive, high-quality data sets that can support the needs of researchers and developers working on advanced diagnostics. And Work Package 3 is also responsible for developing and governing the Big Picture metadata standard, also known as the MSM-DAD. This standard ensures that the metadata associated with pathology images is consistent, high quality, and interoperable across all nodes and systems. The governance of the metadata standard is crucial for ensuring that the data in the Big Picture repository is usable, searchable, and reliable for both researchers and tool developers. So, challenges. There were a few, I can assure you. And in today's interconnected digital landscape, a governing document of sorts for metadata plays a critical role in ensuring consistency, data quality, and system-wide alignment. And different systems or stakeholders may use varying definitions for the same metadata elements, leading to confusions and errors. And for example, with one system from a laboratory in Vienna defines as patient ID may differ from another labs from Linköping, for instance, of the same attribute. So basically different interpretations of the same thing, but with different names. And without a common ontology, and I know that many of you alluded to this earlier also, it becomes very hard to create a standard governing document that aligns these disparate definitions. And different databases, different LIS systems, and other IT systems may have been designed using diverse ontologies, terminologies, or data models, making it very difficult to establish universal metadata rules that apply across all systems. And these differences can hinder, obviously, interoperability between systems and data. And when metadata exists across various systems, each potentially adhering to its own ontology, a lack of alignment leads to challenges in cataloging or even locating the metadata. And in some cases, systems may even have conflicting ontological structures, making it even harder to structure the metadata. And if multiple data sources are integrated without aligning their respective ontologies, metadata may be interpreted differently by each system. If you take an example, one system might follow a very healthcare specific ontology, HL7, for instance, while another might use a more general data model. And this ontological mismatch makes it harder to track where metadata resides across the IT landscape, as systems might classify the same data differently. And another huge challenge is when dealing with large data volumes, such as high-resolution pathology images, several key factors related to infrastructure capacity come into play. Pathology, by their nature, are highly detailed and can be significantly larger than other medical data types. One pathology image can be hundreds or even several gigabytes per file. And managing and storing such large files place a heavy demand on storage infrastructure. Pathology images, due to their size, require significant bandwidth for transfer between systems, and slow network speeds can cause delays in data processing and reduce the efficiency of workflows in the clinical day-to-day reality. And if multiple large pathology images are being transferred at the same time, it can quickly overwhelm network infrastructure, leading to latency, congestion, or even dropped connections. This is especially problematic in real-time or near real-time applications such as healthcare, where quick access to images is crucial for the patients. And one, if not the biggest challenge for us at Region Östergötland, where I work, is how do we actually streamline and automate the workflow from data in our hospital's IT system and the extraction of that data to the conversion of the data into unified format and anonymization at the same time. That was a huge, huge challenge for us. So what approach did we have to overcoming these challenges? Well, the big picture involves multiple stakeholders, including data providers, researchers, developers, and regulatory bodies. Each party brings different expertise, requirements, and challenges, making collaboration essential to ensure alignment and smooth integration. We have created in the project cross-functional teams that bring together experts in pathology, IT infrastructure, and data governance to collaborate on data extraction, sharing, and standards development. Regular meetings ensure that all stakeholders are aligned on these objectives. And we have established clear communication pathways between work package 3, which is my work package, and the other work package. We have representation from work package 2 here. Joel Hedlund, data director at Ada Data Hub. So in that way, we are ensuring that any feedback or issues from nodes or researchers can be quickly addressed. And we have also developed a metadata standard called MSM-DAD, which is derived from the EGA metadata schema. One of our key challenges that I saw when I started at Region Östergötland and I started this journey with data extraction was tracing the data flow from within the LIS, that is the Laboratory Information System, and identifying where specific information was stored in the database. And the understanding of this was crucial for me and for us to realize and understand where we had the values in the database, basically. And as we navigated this complexity of our LIS database, manually tracing transactions became increasingly difficult due to the intricate structure of the data relationships and the sheer number of database interactions. So we leveraged the power of SQL Server Profiler. I don't know if we have any database admins around here, but if there are any nerds here, maybe you know what it is. This proved to be a very powerful tool for us because with that tool, we could trace the data flows and pinpointing exactly where the data was stored. For instance, if we wanted to know some specific attribute of some histopathological value, we needed to know where in the database is that value stored. No one could answer that. We had no clue whatsoever. So we used SQL Profiler, and that was a really powerful tool. And this way we could develop SQL queries that extracted the metadata that complemented the image data that we extracted from the packs. I should also mention that the packs that we are using is modern packs developed by Sectra, and where we had modern APIs, as most of the systems that are developed today are. So that was not a problem at all. But then we had the laboratory information system where we had all the metadata, all the data about the patient, observational metadata, and lots of important stuff. And this system was built in the 90s, and no one knew anything about it. We had no clue where to look or what kind of tables in the database. We knew nothing about it. So that was a huge part for me to map the values in the database to the values the pathologist looked at when they looked in the application. So that was a really big thing for us. And another critical concern we faced was whether or not Region Östergötland's infrastructure had a capacity to handle the additional workload generated by our project without disrupting the normal clinical workflow. We would not want a pathologist, when looking at images, have problem with. No, this is the right one. Yeah,
Oh,
yeah,
sorry,
yeah. No. We're still at the overcoming challenges. Yeah, so. So we wouldn't want to disturb the clinical workflow, basically. When we extract terabytes of data, we don't want to disturb the patients or the doctors, because that would be obviously very bad. So we began by conducting an initial assessment of the current infrastructure and looking specifically at network bandwidth and storage capabilities, obviously, and processing power already in use for clinical workloads. And we then collected metrics on CPU utilization in the system, and memory consumption and network traffic during peak hours when the doctors were working at the most. So we got some kind of baseline system performance there. And this provided a benchmark that allowed us to gauge how much additional traffic that could be accommodated without overloading the system. And we understood that the hospital's IT infrastructure was critical to ongoing clinical operation, obviously. So we collaborated closely with the hospital's IT engineers from the start. And we discussed our project's data transfer needs and what kind of requirements we had, and worked together with them to determine the best approach to ensure that we wouldn't impact the day-to-day workflow for the doctors and the patients. And we actually set it up so that we extracted most of the data during off-peak times, such as weekends or evenings, so as not to disturb the clinical workflow. One of the key milestones in our project in the big picture, I think this is very subjective, but that is the development of a custom extraction tool called SlideTap. SlideTap is designed to streamline and automate the extraction of critical data from the PACS and the LIS. And it focuses on data extraction, but it's also mapping staining information, DICOM conversion, and anonymization. And SlideTap has become an essential part of our data workflow, ensuring that the extraction, mapping, conversion, and anonymization processes run smoothly and efficiently. And by using SlideTap, we can now extract and prepare large data sets for use in the big picture repository without disrupting clinical workflows or compromising on data quality. So now that we covered the challenges and our approach to them, I'd like to take a moment to reflect on the key outcomes and achievements we have accomplished so far in the project. And as I mentioned before, one of the most significant outcomes for us has been the development of the SlideTap tool. The SlideTap is an open source project, and this open source project has basically allowed us to automate data extraction from the PACS and the LIS systems. And this has improved our efficiency by a factor of 10, perhaps, of our data collection processing, and eliminating the need for time-consuming manual efforts. And SlideTap has also successfully handles the complex task of mapping staining information from the laboratory information system to our database and converting pathology images into the DICOM format. And this has ensured data consistency and adherence to industry standards as well. And with built-in anonymization features, SlideTap ensures that sensitive patient data is anonymized in compliance with GDPR, allowing us to work with data securely and ethically. How are we on time? Yeah, okay. Okay, thank you. Another major achievement has been our ability to extract large volumes of data without disrupting the also important clinical workflow for the hospital, the doctors, and the patients. And through careful planning, testing, and coordination with the IT engineers, we have ensured that the additional traffic generated by our data transfer does not interfere with critical hospital operations. And one of the key milestones from a community perspective, I think, is the development of a MSM DAD metadata standard. What is this? Well, this is a standard that ensures that data from different nodes and systems can be integrated into a unified format. This makes it easier to manage, analyze, and search the data within the big picture repository. Because as I mentioned earlier, data from a pathology lab in Linköping does not look the same as data from a pathology lab in Vienna or in Sofia, for that matter. So the metadata standard plays a crucial role in supporting the development of tools and algorithms in other work packages in the big picture project by providing structured, well-organized data that is ready for machine learning and AI applications. And thanks to automated processes we have implemented, especially for tools like SlideTap, we have created a scalable infrastructure capable of handling large data volumes. And this ensures that as the project grows and more nodes are added to the project, our system can accommodate the increasing data without manual intervention. And automation has not only reduced the time required for data extraction, mapping, and anonymization, but has also increased accuracy by eliminating the risks of human error. And this enables us to focus on more complex tasks and ensure high quality data across the board. Overall, these outcomes have positioned us to provide high quality, well-organized data sets that are crucial for the big picture project. And by focusing on automation, collaboration, and data governance, we have laid a strong foundation for future growth and innovation in medical diagnostics and research. So I also would like to give you like a sneak peek preview on what's happening in the project. And one of our upcoming initiatives is to integrate quality control algorithms developed within the big picture project to the SlideTap workflow. These algorithms are designed to automatically identify issues such as distortions, blurring, or tissue folds that could compromise the quality of images, also called artifacts. Once integrated, the artifact detection algorithms could operate as part of seamless real-time scanning of images during extraction. And, this will further streamline the processes by reducing the need for manual sanity checks and speeding up data preparation for uploads. And while the development of extraction tools like SlideTap is super important in the big project, we, as a project and in Work Package 3 especially, continue to push for more data to be actually uploaded to the platform. Yeah, thank you for listening. Yeah.